So welcome you in the last session of today. So today we will basically start with the theoretical as well as the application-based topic. Uh, what is it? That is basically graph signal processing, right? So that would so firstly regarding it, I want to tell you that it is such a significant topic that whatever my PhD work, I began with this topic, and initially I applied this topic in the application of the image processing under the topic facial expression recognition. Later on, I extended this topic with the help of my PhD student in the facial recognition. And thereafter, my even another PhD students who are also attending the courses, like Ram Nivas, he is applying the concept of GSP in the uh, EEG signal. Anand, he is applying the concepts in the wave radar based applications. Sumans, he is applying the concepts of graph signal processing and the basically medical images detection. So it is, I see it's a really a fundamental shift at the signal processing level. So it is very, very important, and we will try to learn it from the beginning. I hope, see, as I have applied it at the different topics, you would also be able to apply it your application, and you would able to get a good publications here. So regarding it, so what is basically the graph signal processing, motivation and fundamental learning graph from observation of a smooth signal, case study, discriminated graph learning for emotion recognition, general utility of graph signal processing, specific utility of GSP and MMA radar, comparative study of DSP and GSP, case study, discriminated graph learning for emotion recognition, conclusion and future scope. Even see, I want to tell you that this topic was actually began in around the year 2014, and thereafter almost every year I have attended its international conference, which was held in the one in Switzerland, another last time in the Oxford. So very, very application based topic, and based upon its utility, the even separate sections in the research journals have been coming where they are asking the application of this concept. So now going into the topic. So first we try to understand, see what is this one. So graph signal processing basically deals with the signals. Uh, Signals whose domain defined by, see, remember two words are there. If you really see, there's a graph and another is signal processing. What do you mean by the signal processing? If you understand the signal processing, as we yesterday we took up the topic image processing, that some operation is taking place at the pixel level, some mathematical operation is taking place. What do you mean by the signal processing? In signal processing, see whatever signal is there, whatever smallest signal you consider, there some mathematical operation is there. So that is the signal processing. Some transformation of signal is there. When you say it means that the signal is processed. What do you mean with the graph signal processing? See, graph signal processing means that the graph means, as we see, now we try to understand what do you mean by this graph. Graph means basically we are also able to see the topology of the signal. How, what type of interconnections are there in a signal. We want to extract out the information from the structure of that signal itself. So this is the key thing. Definitely, if some signal is very, very simple, we are not able to find out much more from its structure. But when some signal is complex, like the EEG signal, like the facial expression, which are basically the multidimensional. There you can see the uh, interconnections are there. So there we will able to utilize it. So what does it say? We first understand the definition that the graph signal processing deals with signals whose domain defined by a graph is irregular. Some simple forms of processing signal on graphs like filtering in the vertex. See what do you mean by the vertex? Vertex basically, for example, we will also go to the diagram. See in the next slide, it you can see here. See, for example, this is basically an image here. The vertex means basically this is the one, two, three, four, five, six, seven, eight. See, these are basically the vertices, right? So what what we are saying at the filtering in the vertex and spectral domain subassembly are given. What do you mean by the processing? See, processing means here, as we saw in the image signal, that operations are taking place on the pixel value. Graph signal is basically collection of point where each point is considered as the vertex. And there we will see that what type of operations are take place on those points. Graph topologies are reviewed and analyzed as well. What do you mean graph topology? Let's see, there are the different structures to interconnect those points. Research in graph signal processing aims to develop tools for processing data defined on irregular graph domain. See what do you mean by irregular? It is not necessary that there is a some regular pattern. See, for example, I take up a 3 point, right? I consider a 3 points. See, one way is there that all the 3 points are connected. But it is not necessary that all the 3 points will be need to be connected. Maybe some 2 points are connected. Third point is not connected to one. So that is not a regular one. So here we say that can we really apply the fundamentals of signal processing? So graph offers the ability to model such data. See, first thing, if you recall the basics of the signal processing, if you recall the initial chapters of the signal processing or the signal and system, first we learn to represent our signal. That how do we represent the signal? For example, xt, xn. uh, what do you mean? How do we represent it? It means we are able to write the different values. How does it make a sense? It means when the value of say, see what does these value convey? These value convey that at t point at t equal to 0, this was the value, at t equal to 1, this was the value, at t equal to 2 unit, this was the value. So it basically explains the change in a signal with respect to the time. Why? So this is the thing. So same way, when our signal is basically defined in form of the graph, how will what will be its representation? That will be interesting to see. Because remember, whatever be the representation, that is the key thing when we find out the algorithm, when we apply those algorithms. So what we are saying, graphs are generic data representation. What do you mean by generic? Means definitely there may be some which can be generalized. Forms that are useful for describing the geometric structures of data domains in numerous applications, including social, energy, transportation, sensor, and neural network. See, even if you will also see the today's different type of network, even if you will also see that today different type of network, for example, you are seeing in this slide that basically the temperature data. In this temperature data, see what you are seeing, this is basically a map. What is this red reason is showing? Red reason is showing that the higher temperature. For example, we can draw a map of the Rajasthan. We can draw a map of the India. So we can also make a such a figure where the temperature of different places are shown. Red is basically showing. So what is important? Important is the one thing that, for example, the places which are nearby to the desert or which are nearby to the Delhi are basically have the higher temperature. So what does it mean? It means there is some relation, there is some geographical relation between the data and the location of those places. In the same way, traffic data, see, you can take example of any city. If you take example of any city, see, what do you see? That some places are very, very crowded. For example, like the main market in any city. So see, what is interesting to observe here, when we see it collectively, we are able to see the different patterns. In the same way, for example, the social network data. What social network data, for example, you take the Facebook, you take the WhatsApp. See, what does this convey? This convey basically this person. This person is basically connected to another person, to another person. So, what do we want to say? That if you really want to analyze any person, it is not sufficient to analyze that person, but also it is important to understand its connection. कि वो पर्सन किस किस से कनेक्ट, फेसबुक में उसके कौन फ्रेंड्स है, क्या है. सो in that way you are able to gather much more information. That's why, so instead of analyzing a one person, we basically consider a network, and this network is the one which is which has the connections, and that is the best way to form a graph. See, is there any difference between graph and network? Can somebody tell? When we are saying that whether the graph and network are same or are they different? So see, if you consider the thing, graph and network both are the same thing. Network only we consider it. It is more than one when more than one elements are there. That is basically both are not same. See how Ruchi has answered both are not same. Can you give example? How are they different? See, if you really see, only it is the context where they are used. That way only they are different. Otherwise, what is network? When more than one elements are there, and when their connections are also taken into account, that is the network. In the same way, what is graph? Graph is also something where you are able to know the interconnection, how one point is connected to the another point, or how one person is connected to another point, how one node is connected to the another node. Ruchi is saying mathematically operation are different on graph and network. See that's what we are saying, that whenever you use a see graph, they will hardly used simultaneously. You will never ever see the case where both are used simultaneously. Only it is the context. Somewhere people are saying when it is more than one element, it is also the network. Where it is more than one element, people are saying graph. So if you see fundamentally at the property level, they are not different. Only it is the context that in some places it is collection of nodes is graph, and in some context it is collection is basically network. Another see point neuroimaging data. See neuroimaging basically it is our brain data. So even in brain also see brain is such a complicated organ, and what is important here that one region governs the functionality of a body, another region governs the functionality of body, but both are biologically connected to each other. When they are connected to each other, so you can't separate out them from each other. They influence each other also. It is exactly the same way, for example, some places there which is nearby to the Jaipur. So if we really consider the language of one place to the another place, they will be relatively similar because of the proximity. So in the same way, what we are saying is, so when we want to analyze the brain data, this interconnection becomes very, very crucial to analyze the overall phenomena. That's why we are very much interested in representing the signal as a graph, whether it is the neuroimaging or the social network or the temperature, because here the uh, neighborhood data makes a lot of difference, or we can say it gives a complete picture. Now, coming to the another thing, see regular data structure. What do you mean the regular data structure? Regular data structure means all where it is symmetry is there. For example, this is basically image. What do you mean by image? It is basically a 4 by 4 image where all the pixel values are there and they are connected to each other in this fashion. What do you mean by irregular data structure? See, irregular data structure here it lacks symmetry. Here you are seeing that the signal something is coming to here, something is going there, but you are not. If you cut out this region, if you take out if you segment out this region, you will find out the different type of segments. All the segments will be different from each other. That's why this is the irregular. So where are you able to find out the irregular data structures? You are able to find out the irregular data structures in the social network. Some person is able to connect with 5% of his college, 5% of his home district. So this way, there is no some any regular thing. Sensor, web traffic, supply chain, because they are instantly, it depends upon the instant situation. Another regular data structure is time series. What do you mean the time series? That, for example, some event has taken place at t equal to 0, then its value, it has changed at t equal to 1, and t equal to 2, t equal to 3, and then this value is there. So what we are seeing on the left hand side, it is regular data structure. On the right hand side, it is irregular data structure. So graph also allows you to process these irregular signals. That's why the normal signal processing, conventional signal processing doesn't allow us to process these irregular data structures. So that's why this graph signal processing is a very, very good tool. Coming to the another example of the graph signals. Remember, now we are dealing with the two words, basically graph, signal, and processing. Earlier, we started with the graph and the signal processing. What do you mean by the graph? Graph means basically the structure where signal processing is based upon the structure. Now, what we are saying that we have understood that graph signal is one thing. We want to understand that what is this graph signal? What do you mean by the graph signal? Graph signal is the one where you are also able to know the structure of the signal, where you are able to represent the signal structure, its component. So how do we represent it? This the automatic question, so that you will see here. See, for example, you are seeing here the sensing points. What do you mean by the sensing points? See, sensing points is basically you are putting some sensor at the different places in a some particular fashion. One sensor you have put here, second sensor here, third, fourth, etc. The sensor may be there to record the temperature. The sensor may be there to record the velocity of air velocity. Whatever the different purposes are there. Another example, it is basically action. What is the sensing location? Again, see some data is there. For example, at point 1, 2, 3, 4. What is this value on the y-axis? It is the magnitude of the signal at point 1, at point. So what we are seeing that these are basically the collection of points, and these collect where at every point the signal has different value, one value which is independent of the another value. Now see, the question comes that how do we represent it? It is the same way we will exactly go through the signal processing as we have gone through the conventional signal processing. So what we are saying here that in the graph, so we are defining the things, basically two things. One is basically vertices, another is length. What do you mean by the vertices? Vertices we define, see, are you, we, see, are you able to see these points, these black points? These black points you are able to, sensors are vertices, correct? Yes, see, sensors are vertices, correct? Even you are able to see these points, these black points. I'm moving the cursor. Are you able to see my cursor? Yes, this is the one. This is basically vertices. This is another vertices. This is another vertices. This is another vertices. Right? Now, remember, over the vertices, one red line is there. What do you mean by this red line? This red line means that what is the value at this vertex? Vertex is basically a number. It is basically 1, 2, 3, 4, for example, this thing. But what is the value? For example, if this is a temperature sensing point, then what is the temperature at location 1? So this value is represented by this red line. Another thing, what we are able to see in the graph, that blue line is there, which connects the two vertices. Are you able to see? This is basically new concept. That's why we are taking time here. So are you able to, is everyone able to notice the this edges? How many edges are there? Any idea? Can you calculate? Question to every participant. Please give the number of the edges in the figure E, which we are seeing. Can you calculate? N into n plus 1 upon 2. What is this n? This is basically when we add up the numbers, which are n are basically vertices. Okay. Total number of vertices. Very good. So yes, so this is basically one of the way that neighborhood nodes. Yes, correct. So see what we are saying here, if you are able to see, this is the basically one edge, this is another edge, this is the another edge, this is another edge. See what is important here, that it is not necessary that every vertices will be connected to everyone. It will depend upon the actual situation, right? So that actual situation we are able to represent. See, for example, we take up the actual example. See, for example, we can see, for example, I have to assess the success rate of any individual in a some college, right? So what do I do? I draw a network where person is also considered as a vertices. His friends, all the means, for example, it's a organization of the 20 people, right? Then what we will consider, that to how many persons is the person interact, regular interact. So the person with whom they are interact, they are connected by the edges. And the person whom they hardly interact, or he or she doesn't interact, then there is no edge. In this way, there will be 20 vertices and some edges will be there. So what we will able to do here, because the success doesn't depend upon the individual's ability or the individual performance, because in an organization when you work together, it is basically the linkage, that how many people are you associated with, how much your good team is there, because it's not only the one person may be very good in one some task, but it is overall how do you function in organization. So there, this graph signal representation becomes very crucial. So what does it say here? It is said, so graph signal. So what do you see? Now we say the, so what do you mean the graph? Graph basically consists of the two words, vertices and the edges, nodes and the edges. Node is basically the single point and the edge is basically the link between those 2 points. What do you mean with the graph signal? See, graph signal, we consider this one. Along when the value is given over these vertices, then that is the graph signal. So what we are saying, set of scalar vector values defined on the vertices. So, so many red lines are there. All these represents the value, because graph only represents the location or the points, but graph signal represents the actual value. So graph G equal to, so how can we represent the overall graph into the G equal to VEW? What do you mean the V? Vertices, edge, and the weight. Remember, edge is there. See, I may be associated to the two people, but with one person, I interact. Uh, uh, we have a conversation, a regular conversation of 1 hour daily. With another person, I have a conversation of 20 minutes. So not only the link matter, not only the edge matter, but how frequently there is a difference between the interaction. So that is taken care by the weight. Then we come to the part vertex set. What in vertex set? Again, we will number it V1, V2, edge set V1, V2. If the edge is defined between V1 and V2, if edge is defined between V1 and V3. And how is the graph signal? X1, X2. So what is X1? X1 is basically the value at point 1. This magnitude X1, this is X2. Are you able to identify the X1 and X2 in this figure E? Can you identify? In the figure E and D? x1, x2 value. In the figure B, are you able to identify? Can you? So voice is breaking. Okay, let me repeat it. Depends on we are doing full graph or neighborhood nodes, vertices. I repeat it again. See what I'm asking. See, I am asking here that are you able to identify this x1 and x2? Here we are seeing that the graph signal is basically a vector, is a collection of these values x1, x2. But from this figure, are we able to find out the value D, E, or C in either of the figure? Krishna, is question clear? See x1, x2, this. See what we are saying. See. Remember here. See, we are not able to know the exact value, but I am able to see. For example, here two things are there. That one, two, three numbering is not there, so it is ambiguous. You can't say which one is x1 and which one is x2. To define a graph signal, you need to number those points. So E, the information in this figure E is incomplete because it will depend that where are you numbering. Whether I am numbering 1, 2, 3 to the upper one or the lower one. See, for example, here I consider that total number of total number of vertices are 30, right? So 30 value will be there. That is sure. X1, X2, X3, X30. But which one will be X1? That we can't say. That will depend upon that which one is the first point. So that is ambiguous. So that is the key thing. So in graph signal, you can interpret one signal in many forms. Numbering will be different. So now coming to the operation on the graph signal processing. Graph Laplacian, we will define some terms. See, tomorrow, see what I will do. I will use basically a board. So what I'm seeing that in the slides, many things are not, we are not able to convey. So from tomorrow onwards, I will also use a whiteboard so that I am able to show you the things very clearly, like whiteboard. So, but So, so what we are saying here, so graph Laplacian, this is basically a mathematical operation. L is Laplacian, D is basically the diagonal matrix, W is the weight matrix. That is central to the graph signal processing. So we will continue this topic tomorrow. Another thing, see, in any signal processing, the key thing is the frequency domain analysis. When in the frequency domain analysis, see what do you mean by the frequency in the Fourier transform in the so here these eigenvalues are considered as the frequency. I will explain you again these concepts on the whiteboard so that you can very clearly see from the slides. It would be difficult. So when we are able to define the frequency concept in a for a graph signal, then we are able to define the another concept like the filtering. So what do we say? That the graph signal is good at capturing structural property. What do you mean by the structural property? It means the things. See, for example, if some signal has structure 1, another signal has structure 2, if we will do the filtering on both these signal, then not only due to the individual values of the graph signal, but also due to the structure, the operation will be different. The graph signal processing will lead to the different outcome. That's why we say that it captures the structural properties. What are the applications? Applications basically video and image problem can be structured as graph. Represent object structure as a graph. Uh, the object structure means, for example, we are taking some figure, we are taking some image. Deep learning, even see deep learning on graph is starting to become more prevalent. So, GCNN, for example, many people who have been using the deep learning concepts like the convolutional neural network, the new concept has come graph convolutional neural network, which is very, very good because it takes into account the structure. Create robust method by denoising signals on graph. What we say that uh, noising means basically, see, we will see that, for example, if I want to eliminate the noise at overall image level, instead of pixel value, then also the graph operations become very relevant. So this is the thing, geographical network. Again, see, as we have already seen that the network and graph both are same here. So what we are saying that the it is geographical network. See, for example, if I want to analyze the places, for example, see, for example, during the COVID time, if you would have observed that how the how the this COVID has been increasing. This is based upon the regions also. क्योंकि एक प्लेस से दूसरी जगह कनेक्ट है वहां कितने लोगों का माइग्रेशन इधर से उधर है दैट बेसिकली that decides the number of patients. So at that level, this geographical network or the structure makes a lot of difference. In the same way, social net. So what we are saying, we have also seen another diagram, but here we are able to. So what we are saying, graph provides a mathematical representation of network. Means network is basically some collection, but graph is basically which is related with the representation. What type of representation? Two type of representations are there. One is basically the vertices, that which vertices are there, and the linkages between those vertices. Whether one vertex is connected to the another one. So this is the one. So I think this is till this point, and so yes, if somebody is very want to make a difference, as like Ruchi has mentioned, so yes, in a graph we can say that method it is a mathematical representation. To make the things clear, we say that graph basically consists of the three things: vertices, edges, network. Vertices, edges, weight. In our this analysis, otherwise, so this will be the minor difference between the graph and network. So here I conclude it. Tomorrow onwards, I will try to explain this topic not only with the help of the slides but also on the whiteboard. I think that will make a more meaning. And see, please enjoy this topic. This is a new topic. but I'm telling you, it's a lot of potential for the your research. To my every PhD student, see, I am only doing research, whatever it is based upon the graph signal processing, because see, one thing is very much, one fundamental is very clear that if you analyze the signal without this structure and if you analyze the signal with a structure, definitely the signal with a structure will provide you a much more information in comparison to the earlier one. यदि मैं केवल आपको एनालाइज करके देखूं कि आपकी कैसी परफॉर्मेंस है, इट वुड बी वेरी डिफिकल्ट टू अंडरस्टैंड। पर यदि मैं उसी की जगह मैं ये देखूं कि आप कितने लोगों से, आपका नेटवर्क क्या है, आपकी कंपनी क्या है, हु आर योर गुड फ्रेंड्स, आपकी फैमिली में कौन है, या मैं ये कहूं कि जिन लोगों से आपकी मोबाइल पे ऐसे लोग जो 10 लोग हैं, मैं एक नेटवर्क बना लेता हूं और उनका मैं ग्राफ बना लेता हूं कि वो लोगों में कितना पोटेंशियल है। आई एम टेलिंग यू, वो जो 10 लोगों के साथ, वो 10 लोग हर एक पर्सन के, जिससे वो 10 लोग कौन से हैं जिनकी आपको सबसे ज्यादा बात होती है मोबाइल पे, वो लोग अच्छे हैं बुरे हैं, इट विल बी वेरी मच कंट्रीब्यूटिंग इन योर परफॉर्मेंस। आप चाहे कितने ही इंटेलिजेंट हो, आप कैसे भी हो, बट इफ आई सी द इंफॉर्मेशन एट कलेक्टिव लेवल, इट विल बी से वी से इट विल बी वेरी एनहेंसिंग। एक मैं यदि इंडिविजुअल पर्सन को देखूं तो इसीलिए फॉर एग्जांपल सी आई टेक द केस, फॉर एग्जांपल आई सी द केस कि यदि मुझे आज एक कंपनी को एक उसमें लेना है, फॉर एग्जांपल दे हैव टू सेलेक्ट सम कैंडिडेट, उन्होंने एक पर्सन का वो देखा, उन्होंने एक पर्सन की इंडिविजुअल परफॉर्मेंस देखी, दूसरा उन्होंने ये देखा कि उसने कौन कौन सी वेयर इन हाउ मेनी सेक्टर्स और विद हाउ मेनी पीपल दैट पर्सन हैज वर्क। यदि so that information would be much more enhancing in taking that person। पर क्या अभी प्रॉब्लम क्या होती है? अभी प्रॉब्लम यही होती है कि वो सब इंफॉर्मेशन इतनी लेनी इजी नहीं होती। हम किसी से ये कह देंगे 10% बिकॉज इट इज बिट टाइम कंज्यूमिंग, बट यू विल सी डेफिनेटली इन द फ्यूचर कि जब भी हम बात आएंगे तो केवल हम किसी भी चीज को एक कलेक्टिव लेवल पे देखेंगे, ग्रुप लेवल पे देखेंगे। So this is here I conclude or I say I conclude the today's part, today's introductory part of the graph signal processing. We will come this topic very potential topic for the research one, it for the our V signal processing people. Many questions. सी अनदर एग्जाम्पल यू कैन सी, एक क्लासरूम में यदि आप आएंगे तो क्लासरूम में क्या होता है, आप देखते हैं एक ग्रुप लेवल पे इंटरेक्शन होती है, वन पर, तो देयर द क्लासरूम लर्निंग इज वेरी डिफरेंट। यदि आज हम एक इंडिविजुअल से बात करते हैं, व्हेन एवरी पर्सन इज ऑलमोस्ट डिफरेंट, यदि वो किसी को, एवरी पर्सन इज इंडिविजुअल इन हिज इंटरेक्शन, यदि यही लोग यदि आज क्लासरूम लर्निंग में आते, यदि ऐसा पॉसिबल हो पाता, हम वी विल ट्राई इट ऑफलाइन, तो आप ये देखिएगा जो आपने लर्निंग कंटेंट है इट विल बी मच मोर डिफरेंट, जो रेट ऑफ लर्निंग है वो कहीं अलग होगी। सेम टीचर है, सेम मैटर वो कम्युनिकेट कर रहे हैं, पर यदि जितने भी आप लोग हैं, जितने वेदर इट इज द फॉर एग्जांपल हियर राइट नाउ इट इज 11 पीपल ओनली, टोटल 30 पार्टिसिपेंट, यदि उन 30 पार्टिसिपेंट्स को हम क्लासरूम में आज लेते हैं तो लर्निंग एट वुड बी अ डिफरेंट लेवल। सो दैट इज वी आर सेइंग कि ग्राफ structure makes a lot difference. So I'm waiting for the questions. If you, anyone, if you have. So regarding the material, so we will share it. So yesterday's slide, you will able to get it. And Pachori sir, as he will come again, he has gone for some emergency work. So I will ask him tomorrow only so that he can give a slide. You will have access to those slides. Whatever the people are teaching from, you will not have a problem of the material. So thank you to everyone.